Welcome to CADI Medics. This tutorial is on the oxygen hemoglobin dissociation curve. This curve is the relationship between the hemoglobin saturation of oxygen and the partial pressure of oxygen in the blood. We'll start from basics and label the axes. So on the x-axis we've got the partial pressure of oxygen, and that's measured in kilopascals. It can also be measured in millimeters of mercury. So on the y-axis we've got hemoglobin saturation, and that's as a percentage. So the curve looks like this. It's a sigmoid shaped curve, or an S-shaped curve. And the reason it's this shape is due to a phenomenon called positive cooperativity. To understand positive cooperativity, we need to have a better understanding on the structure of hemoglobin. So, the structure of hemoglobin consists of two main things: the heme part and then the globin part. So we'll talk about these individually first, and then we'll bring them together at the end. So with the heme aspect of hemoglobin, this consists of an iron atom in its ferrous state, so in its Fe2+ state, bound to a porphyrin ring, which is an organic ring-like compound. And then you have the globin aspect of hemoglobin, which in adult hemoglobin consists of 4 polypeptide chains. You have 2 alpha chains and then 2 beta chains. So now I'll draw the structure of hemoglobin, but just remember it's just a diagrammatic representation of hemoglobin and not exactly what it looks like in terms of its structure. So we'll start off with the globin chains, and specifically the 2 alpha chains, which I'll draw like this cloud-like structure. So you have 2 alpha chains, and then you have 2 beta chains, and I'll draw the beta chains like this. So we have 2 alpha chains and 2 beta chains. Now each of these polypeptide chains is bound to a heme group, which consists of the Fe2+, so iron in its ferrous state, and porphyrin, or the porphyrin ring, which I'll draw using this coloured in square, and it just represents the porphyrin ring, just to make it easier to visualize. So as there are 4 polypeptide chains, you also have 4 heme groups, which also means you have 4 parts of adult hemoglobin where oxygen can bind, because the oxygen binds to the heme groups to form oxyhemoglobin. So that's the structure of hemoglobin. Now, positive cooperativity essentially suggests that the first oxygen that binds to adult hemoglobin is the one that is the most difficult to bind, while subsequent oxygen molecules are a lot easier to bind. So if you have 4 oxygen molecules, and this is the first one to bind, that's the second one, that's the third one, and that's the fourth one. The affinity of oxygen, so how avidly oxygen binds to hemoglobin, increases as you go from the first oxygen to the fourth oxygen. So just a reminder, the first oxygen is the most difficult one to bind, the second one is a little bit easier, the third one's a lot easier, and the fourth one's the easiest to bind, which is why you have this S-shaped or sigmoid shaped curve. So here you can see it's quite difficult to bind, then it gets a bit easier, then a bit more easier, and then the easiest one there. So that's positive cooperativity. So the next part of this tutorial, I just want to talk a little bit about what we mean when we say the curve shifts to the left or the right. Now, in general, what it means for the curve to be shifting to the right is that the hemoglobin at a given partial pressure of oxygen will have a reduced affinity to oxygen, which means that the curve shifts to the right in any cases where the tissues will need the hemoglobin to release the oxygen. Okay, so if we, to use an example, if we take the P50, which is the hemoglobin saturation at 50%, okay, and we follow that to our normal curve and say that this partial pressure of oxygen will be 3.5 kilopascals. If we follow this where it hits our blue curve, which is the curve that's shifted to the right, we can see that the hemoglobin saturation is a lot lower. Let's take it to be 30%. Okay, so that shows that at a given partial pressure of oxygen at 3.5, the hemoglobin is only 30% saturated when the curve shifts to the right and 50% saturated in normal circumstances. That means that the hemoglobin has a reduced affinity for oxygen. And those sort of times where that actually happened are cases where the body needs the oxygen to be released. So that would include things like an increase in PCO2, so the partial pressure of CO2, increase in temperature, in acidotic environments, so that would mean situations where you have a high H plus ion concentration, or otherwise can be known as a low pH. So high levels of 2,3 DPG. You might see that being written as BPG as well. So this is just an intermediate of glycolysis, which binds to hemoglobin, and particularly the beta chains in hemoglobin, to reduce the affinity of oxygen to that hemoglobin molecule. And as a result, it will release hemoglobin. Okay, so these are some of the situations where you have a right shift. So I normally learn it as it's everything that goes up shifts to the right. Now, the only caveat to that is that a high H plus ion means a low pH, so just be wary of that. Okay. Conversely, if you have that same partial pressure of oxygen of 3.5 and take that up to see where it would hit the curve if the curve had shifted to the left, you'd notice that the hemoglobin saturation is a lot higher. So let's take that to be 70%. So what that shows is that if the curve is shifted to the left, hemoglobin will bind to oxygen more avidly, so it would have a greater affinity to oxygen. And these would be the opposite to the right shift. So that would be a decreased PCO2 or alkalotic environments, or a decrease in 2,3 DPG, or a decrease in temperature. So I learned that with, these are all the things that are going down. Again, just be careful with the H plus ion, because a low H plus ion means that the pH is higher. Okay. Thank you for watching the tutorial on oxygen hemoglobin dissociation curve. I hope you enjoyed it and I hope you learned something. I'm just starting this channel, so if you did enjoy it, please like and subscribe. It would really help me, and I'd really appreciate that. So thank you very much and hope you have a good day.